Good morning, everyone. This is Jim Chastain with EasyPower. This is the last in a series of refresher installments that we focused on device coordination. And in some regards, it's not nearly enough time to accurately address all aspects of the topic. But again, what we're trying to do is focus on the tool use, not specifically on engineering-related questions. And as you run into issues that either weren't covered or you have other questions on, you're welcome to send emails or inquiries specific with specific questions to techsupport@easypower.com. As far as this particular webinar, we're trying to limit it to 30 minutes. And if you have questions that come up during that time, you're welcome to send via the question poll entry or the chat line, and we'll see if we can answer them at the tail end. For now, make sure that we have audio going out to the audience. If you could send me a brief chat that you're hearing me, that would be good to know so we're not wasting a lot of time. Okay, the previous 4 sections were basically divided up to an introduction and then toolbar usage, talked a fair amount about sequence of events and how the curves for each element look and can be modified by entering device data for that device, for that element. Part 3, we started looking into the connection between short circuit calculations and how it interrelates to the requirements or the controls in protective device or TCC plots. Last week we talked about, part 3, we talked about voltage fault currents and putting tick marks, custom tick marks on the curves so we could see all arc fault levels and asymmetrical and symmetrical voltage fault currents. Last week we talked how to manipulate the plots, shifting the curves, also putting additional devices on the same plot to see what alternatives an engineer might have as far as mitigating energy. So today we're going to wrap up with a Cliff Notes version, very briefly touch on more in-depth information on the transformer curves, which we promised earlier and didn't get to it, and then address briefly the series coordination capabilities in molded case circuit breakers, and then finally do a once through the PDC, the protective device coordination process in kind of big picture steps, and see if we can address some questions after that. So according to the ANSI standards in C57.109, the thermal damage curves, or rather the damage curves that can be plotted in the TCC format for a transformer, are broken into 2 parts, or have 2 different sections. The infrequent damage curve, which is caused by thermal stresses on the transformer, basically end up being at the higher current levels and for longer periods of time. And these will cause thermal damage, and basically you never want that to happen because it might be something that can't be repaired or accommodated, at least in the field. Likewise, there's a section of the curve that's referred to as a frequent fault curve. That's due to mechanical damage, and these are related to shorter, higher current bursts of energy. And over the course of the life of the transformer, it could actually survive excursions into this area, but it's limited and based upon the size. The number is based upon the size of the transformer. In either case, an engineer wants to accommodate this and be aware of where these fall, these set points fall in his circuit. So let me kind of jump into the EasyPower plot, and we can talk a little bit about this. So here we have a transformer that we've constructed in our database editor. It's a delta Y type of construction. If we highlight it and go into coordination, you can see we plot the TCC, and as we were discussing, this is the essentially the frequent fault or the infrequent fault curve, which you really never want to exceed. This is plotted usually by default because these three check boxes when we set up a new device are all filled in, but it's plotted with this first line, and as I uncheck it, it removes it from the curve. Likewise, if we want to include the frequent fault curve, we would apply and check this checkbox, and you'll see that it modifies the dotted line to be able to indicate where that susceptibility is and the area of concern in the curve. One point to note is the full load current indicated on the TCC is actually based upon either the rated kVA or the overload kVA. Sometimes these may be the same value and sometimes different, but as we indicate and apply one or the other, you can see it changes the rating that we have set up for maximum full load current in the transformer. Okay, one other point is if we're using or if we're expecting a ground fault in the, or we're trying to protect a ground fault in the curve, we have to look at essentially the protection of the transformer and a little bit of a different mode if we have a grounded fault on the secondary. So all of the protection devices that are set up for transformers are based on through faults, which means they're not internal faults or something that happened on the secondary side. And as a result, what we're plotting, at least on the full load currents, is the curve we just demonstrated. However, with the delta Y transformer, if we have a single line to ground fault on the secondary, what we actually see on the primary is the sum of two phases which go through a single winding. And again, this is something we need to protect because this is essentially a double dipper in terms of the magnitude of the current. And so that requires a special consideration when we're doing the plot on the TCC curve. So let's kind of go back to that. And what we're talking about is if we're looking at a single line to ground, a single phase to ground fault on the secondary, we may want to look at this 58% mark, which would be the primary current. And as we apply that, you see the curve now is plotting a different plot, which is 58% below the levels that were predicted or indicated for the 100% load current. Okay, again, that's a special case condition, and it's specifically for single line to ground on the secondary and anticipating the damage or the current that's going to be flowing in the primary side of a delta Y. All right. Then if we take that a step further, we also have the need or the concern if we're using a delta-delta transformer because it's not going to be this kind of a ratio. It'll actually be closer to a 1-to-1, but there still is some need to deal with the short in a delta-delta configuration. So let's close this curve. And the reason I want to kind of focus on this is because it brings up another element of the tool's capability that may not always be obvious. All right, so all I have to do is get to the right example. So what I want to do is put the same transformer in play. And I need to do this in the database editor. Let's save the changes, put in another transformer. And I'm going to copy and paste this transformer into the same place. Again, this is not the way you necessarily design things, but for purposes of demonstration. So I'm going to paste this into this location, but now instead of a delta Y, I want this to be a delta-delta. Now, in normal applications, this is not something you want to see in a circuit. And so you'll see as I go to my short circuit focus, the tool says, hey, you got a problem here with phase shift. And normally this is caused by a delta Y in parallel with a delta delta. So the option that deals with this is under the options schedule, verify phase shifting with system integrity. Normally you want to leave this engaged if for some reason you're looking at a circuit that you absolutely know what's causing the fault and it's not a concern at this time. And frankly, it could actually happen in real life systems where something's operating and for whatever reason there's a reference to utility buried somewhere down in the bowels that causes this fault. You may be inclined to disengage that particular check. In this case, I know I'm not going to be designing a system, so I can allow it to look at or allow it to go ahead and analyze the system even though I know I have a phase shift difference. All right, the point I'm trying to get to is now if I go to the coordination focus, we plot this curve. Now it's a delta delta. The tool knows this, and as I open it up and then plot this unbalanced curve, you'll see now instead of a 58% difference, it's looking at an 85% difference between these two plots. So this would be what's used on a delta-delta comparison. Okay, next subject, molded case circuit breaker coordination. So by default, molded case circuit breakers have a limited amount of variability and flexibility as far as setting their trip settings. It turns out though in some cases there is ability to coordinate breakers if it's been confirmed by testing, and this generally pretty much guarantees that to be able to invoke this you have to have both breakers, the upstream and the downstream breaker, manufactured by the same manufacturer. For the most part, people don't test other breaker manufacturers' product with their devices. So what tests are showing is that the breakers will be able to coordinate even if the curves intersect. And this is set up under the PDC options, and the tools give us an indication of this, but you kind of have to need to know where to look, and honestly it gets a little bit confusing unless you work with it frequently. Case in point is that we're going to be looking at a circuit, in fact here, where we have an upstream square D breaker and a downstream square D breaker, and we're trying to figure out how if these two breakers will coordinate, especially if we've already compared the curves and they overlap. And so in the library, we have the ability to look up under specific manufacturer for a molded case circuit breaker, in this case the style RG, and we can see that for certain sensors and certain current ranges, and I'll show you this in the library, if this is the upstream breaker settings, then the downstream breaker that's selected to these parameters will coordinate up to a maximum current. And again, I think it's confusing enough that you need to work with this before this is a slam dunk. But let me kind of walk through this process real briefly. Let me get to my other example. All right, so we have an upstream breaker, a downstream breaker, and what we want to do is look at how to pick these particular devices out of the library. So if we go in and open the library, so I came in under the little E icon on the top left, open device library, it gives me standard lib, which is the library that most installations are working with. And as we open it up, this gives us a listing of all the device families in the library. So we're looking at molded case circuit breakers, AC, and in this case specifically square D. And we already know we're starting with the R frame. And as I pull it up, we're looking for series coordination and what has been tested by square D that correlates in this particular family. So what we see here on the left column, vertical edge, is the voltage range. And in this particular case, we're working with 480 volt breakers. We can see that if we have, let me kind of go back to the top. If we pick out an upstream breaker with this amp rating and sensor and trip capabilities, then the downstream device, if it's selected from this particular column, will coordinate in spite of apparent overlap or interaction between the curves. So if we're looking at a 480 volt RG 2500 amp sensor in the range from 400 to 600 amps trip point, it will correlate with a square D D-frame DG type breaker up to 35,000 amps. So I started with an RG, I think I was in the 400 amp range. So somewhere in here, and this is kind of where my example lay. So what this is saying is that if we pick a sensor with a 1,000 amp sensor set between 300 and 400 amps, then it'll correlate with an SST LE breaker downstream. Let me see how successful I was at doing that. And again, this is something that's non-intuitive in my regard. So I've picked a breaker here that's an RG style. We have a 1200 amp sensor. We've picked out a 600 amp plug. We've made sure it's in the catalog, and we've set it up for 570 amps with a short-term pickup of 2800. So as we plot that, and what we're told is it should correlate with an LE breaker downstream. And so as I selected that, it's square D SST breaker type, which gives us the ability to set up an LE type style breaker with a 400 amp sensor and plug. It's in the catalog or in the library, and we're setting up for, in this case, 200 amps. So let's see if we can correlate it. So I'm going to just pick out, in fact, I've actually got this already plotted. So we're going to enter coordination. And as we plot this particular curve, what we're showing is this actually, the downstream curve is BL3, and I'm not concerned about that in this particular case. So we're going to take it off the screen by selecting it and deleting. And it just removes it from the plot. So now we can see where BL1, although it looks pretty close, and I probably need to adjust this a little bit, it looks like I probably can get correlation between, at least at the lower currents, where BL2 will trip before, on a downstream fault, before BL1 will trip. And to that end, if we fault this current, fault this bus, we plot a, get rid of BL3 again. See if I can't put on a arcing tick mark. All right, so here's where my bolted fault current will occur. Excuse me, my arcing current will occur. I'm going to pick up this breaker and see where we have a trip differential. And you can see there's enough overlap here. It's not giving me a differential trip. Okay. All right, so at this point, looks like we've got correlation, or coordination above the current. So here's my differential, and it's actually showing potentially that the upstream breaker will trip before we'll start to pick up before we get guaranteed clearance on the downstream breaker. And according to the data sheets, the manufacturer is saying that there's a very good possibility that they will coordinate and the downstream will clear before the upstream actually completes a trip. Okay. And I kind of plotted this earlier after playing with it. Let's see what I did there. Yeah, same result. All right. Again, if you have questions on that, you're welcome to contact tech support at easypower.com. And I'm moving on to the procedures for doing a full-blown protective device. Let's go back to the PowerPoint. I'm going to check on, okay, the baseline for doing protective device coordination. You want to start with the clean one line. You want to make sure that you can produce and calculate the branch currents by faulting the buses. Then we want to enter coordination focus, start with the load and take the first set of protective devices above the load. If you have concerns about what order the protective devices are going to trip, use a sequence of events to verify the device is in play. Then you verify that you have short circuit arc flash control settings, which is in short circuit, and I'll touch on those real quickly. Go ahead and plot your TC curves, make the adjustments to isolate the largest bus load downstream, and then gradually move upstream 2 and 3 devices at a time and coordinate upstream against what you fix downstream. So let's see if we can make that happen. Should have an example here. Okay, so here's an example that we use from time to time. We see on this particular bus that though we have a large motor, we may potentially even have larger loads inside the MCC. So let's go ahead and make sure we can change focus to arc flash. We calculate bolted fault currents, and apparently there's some reason to believe that incident energy may need some optimizing as we look at the different places on the curve. The one circuit that we obviously have, well, so as far as checking the settings for short circuit and arc flash hazard calculation, you do that under short circuit options. And what we're talking about is the arc flash hazard controls. A couple of main things you want to check on. First of all, you're using the IEEE 1584 by default. The model is the basis for compliance. So we're checking worst case arcing current at 85 and 100%, which is standard recommended from IEEE. And generally, you're going to want to be able to include the main breaker on any particular panel as long as you have isolated separation between the upstream bus from the main breaker and the downstream bus, which will be the reference point for doing arc flash calculations. So once all that's been confirmed, what we want to do now is coordinate the safety devices here, the protective devices here, with this first level of breakers coordination, breaker trip settings. We go to the coordination module, we selected the panel and the upstream breaker, and we plot them. And so what we have here is, here's the breaker that's actually probably upstream of the main of the load. Here is the load that's within the panel, and for right now what we really want to see is it looks like this is a molded case circuit breaker, and it's probably set up as well as it can be, but again, this is downstream from the main breaker, so we're really not concerned about this in terms of the arc flash protection. It is important that this be set up where it is with respect to the motor start curve, and so as long as we've confirmed that, we can take that off our plot. The next step that we're trying to deal with is make sure that our main breaker now is coordinated with the upstream breaker, and it looks like the main breaker will not trip on a normal starting curve. I'm looking at this purple crosshatch here, and if we fault the bus, and insert an arcing fault current, we see that if we were to get a fault on the main, on that MCC panel, that its 100% current would be at this level. So the next step in device coordination is to make sure that we have separation, adequate separation between the next upstream breaker and this unit. So we use our difference calculator, and at the 100% arcing current value, we see we have a separation now of about 40 milliseconds. And in terms of what's recommended, what's required, that could work. Whether or not we want to mitigate any of the energy that's involved, it looks like in terms of this breaker, which would be the result of this calculation, it seems to be adequate for protecting the downstream panel. All right, we can save that particular plot if we're happy with the results. There's also some plots here from other cables that are downstream and may not necessarily impact what we're talking about here, but that's something to be aware of. So let's close this plot. We may want to save it, in which case we would just enter a name for this particular plot, and it would be entered and be able to recall later. Then at that point, we know this breaker has been set up properly, so we'd select it and just move back upstream further. This breaker, this transformer, and this fuse, plot the TCC. Now, we know the downstream breaker is set where we want it to be, and what we want to do is fault this bus, again, which will be upstream from this breaker, but downstream from these other units, these other devices. We also have the transformer shown here, and clearly the way this is currently set, there's no protection from either the fuse or this breaker for the transformer. So based upon what other requirements we have, we might want to make some adjustments, show our voltage fault arcing current for this breaker. So again, we faulted this bus, and so now we're looking upstream, which is the breaker I have in green now. And here's my voltage, my arc current for that bus. Where's my separation between the next device? So I pick out, hold down shift, select both curves, and at the voltage fault current, we have a separation of 32 seconds. Okay, that brings up the question about whether or not this fuse is adequate, but at the same time, there may be some concern about whether or not this particular breaker settings are protecting the infrequent fault of this breaker, of this transformer, because you can see we're not clearly protecting it from a possible excursion from thermal damage from higher currents, or rather lower currents at higher time settings. Okay, so this would now involve a discussion between engineers on whether or not this is acceptable protection for the transformer, and then proceed to the next combination of protective devices. Let's not save this, which would include the upstream breaker. So let's assume we've got that setting, and now this, we plot the curve. And here's the relay now that's been pulled into discussion. So we start the whole process over and modify or make adjustments to the relay so it's protecting or filling in the places that may be, and clearly what's set up here is between this breaker, which is BL2A, this relay, which is the system total system protection, and this particular fuse, there could be an intentional miscoordination based upon what's required for the system. But again, that's left up to an engineering discussion and something needs to be reviewed as you're looking at the curves. All right, so the intent here is to show the capabilities of the tools. Have no idea how you would handle this situation in the real world, but certainly if that's something you'd like some technical advice on, our engineering services group would be happy to look at your one-line diagram and advise what your alternatives are or help you do a more in-depth analysis.